Morning. We're going to start with our first talk, and I'm going to introduce Caleb for this talk. So Caleb, come here. So Caleb is a speaker, developer, painter, gamer, and an eccentric, eclectic. Is that the word? What does that mean?
Means crazy.
Crazy. Okay, he's crazy. Yeah, sounds about right. Caleb is currently coding mostly in Ruby and Go. He's not a fan of the SPA. He has braved the wintry tundra of Alaska and the harsh deserts of Arizona. And he has fired a mossy nagant without blinking, fought the Red Menace, built Battleship Couch, and killed the bear. Yeah, killed the bear?
I killed the bear.
Oh my god. Like for sport?
Yes. Well,
No, I like you. I was starting to like you. What happened? He enjoys fine wines and craft beers and punching comments. So let's give him another round of applause. He's gonna start with the game.
This talk is not for people who study computer science. If you know what big O notation is, I'm not going to teach you anything. You can fall asleep now if you'd like. This is for you folks who call sort on an algorithm, and you don't know which demons are moving your strings around in an array, but you get that array back sorted, and that's pretty cool. To understand what Ruby or Postgres do when you call sort on an array, we need to talk about algorithms. It's sort of a scary word, but all it really means is a set of step-by-step directions to complete a task. A recipe for chocolate chip cookies is an algorithm. I didn't have to understand the chemistry and gastronomy of the instructions. When I realized that this was a good example, I just found a recipe online for chocolate chip cookies, and I made a batch following the directions. And then I ate them. All of them. Before we get too far, I want to talk about Big O. Big O can be a scary concept when you see it written out. I usually assume that it's something for math people, and I build websites, so that's not me. But when it comes down to it, Big O isn't really all that intimidating. It's an answer to how fast is an algorithm. And it lets us compare that answer to other algorithms. It's based on the assumption that the basic operations involved in an algorithm are going to take the same amount of time, regardless of what algorithm is using them. And it allows us to compare using a number of operations as a function of the input instead of the actual time to complete. Let's take a look at a couple of algorithms for cutting squares from paper. This is from Amy. It was fantastic. So, from this piece of paper, I'm going to cut out 16 squares. And every time I end up with another piece of paper, that's one operation. So, let's take a look. That's one. Maybe you can help me with the counting. I'm really bad at this. The most efficient algorithm right now. Only one person bought any count anymore. I'm very sad. All right, so 15 operations, and we got 16 squares. So that makes this a linear time algorithm. And it's represented by this notation, order of n. It's read order of n and it means linear time. So if I wanted to cut out 32 squares, it would take me 31 cuts, basically twice as long. Even though the number isn't the same as the number of squares, we call it order of n because the growth is linear. You're probably wondering what this O function is. Here's the secret. It doesn't mean anything. We call it big O notation because we put a big O in front of it. That's it. All right, so let's look at another algorithm. It's the same rules. Every time I get another piece of paper, that's one algorithm, or one operation. And I had 16 pieces of paper. I could count them, but you don't want that. This new algorithm took only 4 operations to cut out 16 squares. So that's big O of log n time, order of log n. If I wanted to double that to cut 32 squares, it would only take me 1 more operation. The difference between logarithmic and linear growth is pretty impressive. This is a chart of some of the common big O notations. On the x-axis, we have n as the size as n grows, and on the y-axis, we have time complexity. Order of n and order of log n are down at the bottom, now orange and yellow. Yellow you can't actually see behind the green because it's so close to just constant time, which is order of 1. They're much smaller because I changed the scale from 1 to 1, which we saw here and here, to 10 to 1, so that we could show how big some of these much larger growths are. Sounds like cancer. That's n factorial, 2 to the n, which is polynomial time, and 2 squared, which is quadratic time. If you draw an imaginary line diagonally through this, then what you want to shoot for in an algorithm is below that line, and anything above it is going to be sort of slow. If we zoom back into 1-to-1 ratio, you can see that even these more performant operations have a lot of variation. That's why order of n was so much faster than order of log n. Okay, so that was technical, and I apologize for that. So I have a couple of jokes. When do you update a user record? On login. If you understood everything so far, I'm really on it today. How do you debug an app? You start logging. What happens when you buy something? Well, obviously you own it. We're also going to talk about big omega. This one is easy. It's exactly the same as big O. But instead of talking about the worst case, or upper bound of how much time an algorithm can take, it talks about the best case, or lower bound. That's why it's got the little lines down there, because it's the lower bound. So I've asked 5 people to help me out. If you could come up onto the stage and join me over here. The bulk sort algorithm is nice and simple, so it's a great place to jump into sorting algorithms. The algorithm is this. Consider each pair of elements, in this case Rubyists. If they're in the wrong order, then swap them. And then you continue. Consider the next pair of elements, and if they're in the right order, swap them, otherwise, or if they're in the wrong order, swap them, otherwise, continue. And keep on doing this until you run out of Rubyists, and then you start over at the beginning. You can skip the last one on the next iteration because you know that it's in the right place. Once you can get through an entire pass without making any changes, you know that you're sorted. All right, so first round of applause for our helpers here. This is pretty easy. I need you to hold up a number of fingers. So you're going to need 4. 4. 5. 3. 1. And 2. Awesome. So we're going to sort these Rubyists, and when you're sorting something, it gets a sorting hat. So we're going to go through this algorithm together. So the first step is compare a set of 2 elements. So we're going to compare 4 to 5. 4 is less than 5, so these 2 elements are in the right order. The hat moves. All right, 5 is greater than 3. So these 2 are going to swap positions. Wonderful. The hat moved, so we don't need to move it again. 5 is greater than 1, and so these 2 are going to swap positions. And finally, 5 is greater than 2, so they're going to swap positions. Awesome. So 5 is now sorted, and the sorting hat moves over to the beginning because we're going to keep going until we don't need any moves. All right. 4 is greater than 3, so they're going to swap positions. 4 is greater than 1, so they're going to swap positions. 4 is greater than 2, so they're going to swap positions. Not until I tell you. All right. We don't have to compare against 5 because we know it's already in the right order, and so the sorting hat moves back to the beginning. Everybody has lice now. Okay, so again, we're going to keep going. 3 is greater than 1, so we swap positions. 3 is greater than 2, so we swap positions. Awesome. Now 3, 4, and 5 are all sorted, and the hat moves to the beginning. So 1 is less than 2, nothing changes. And 2 is less than 3, and it's the end, so we're not actually going to compare it anyways, and so nothing changes. So now we've gone through an entire set without making any swaps, and we're all sorted. Round of applause for our team. Okay. Hopefully painless. It'll be itchy later. So bubble sort works in quadratic time, or order of n squared. And for the purposes of sorting algorithms, n is always going to be the length of the set. Bubble sort is quadratic time because it compares every element to every other element in the worst case. Even though we have some optimizations so that when we're not actually comparing every element to every other element every time through, because we didn't have to check 5 and 4 and 3 the second times through, when we're studying complexity, we still say quadratic time because we're talking about the growth and not the actual numbers. For bubble sort, quadratic time is also the average case, such as on a randomized array. So because we had length 5, the worst case scenario, n would have been 5, and the worst case scenario would have been 25 operations, which include checking and swapping. The big omega, or lower bound, for a bubble sort is n, order of n, linear time, which means that in the best case for bubble sort, it's 5 operations. So if I had said 1, 2, 3, 4, 5 instead of 4, 5, 3, 1, 2, then it would have been 1 is less than 2, 2 is less than 3, 3 is less than 4, 4 is less than 5, and 5 is the last thing, so we're done. And that would have been the entire algorithm. As we saw before, n squared isn't really all that great. It's this big red line, and like we said, we had that diagonal line, and that's above where we want to be. Because it means more operations, and that usually means more time. So what we want to be is one of these 4 smaller lines. Order of n log n, order of n, or ideally, order of log n, or even order of 1. Order of 1, which is constant time, only works in a perfect world where every set is already sorted, and so the only sorting algorithm is return the sorted set. It's useful to see a visualization of some of these sorting algorithms as they work on different types of inputs. Topple has this great set of visualizations that show bubble sort working over different types of inputs. They can help you sort of build an intuition around how bubble sort will work with different sets of data. The red arrow is our subject, which we were using the sorting tab for. Dark bars are already sorted, and light bars are yet to be sorted. We have random, nearly sorted, reversed, and few unique sets. This takes about a minute to finish, because bubble sort is not a very great operation, so we're not going to watch all of it. Insertion sort is another really great algorithm. It's very efficient at sorting small sets. Insertion sort is so called because it inserts the subject element into the subset of already sorted element, blah, 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 blah. That's terrible. Let's take a look instead. For this algorithm, for each element, we're going to consider all elements to its left. Continue until you reach one that's smaller than the element that you're looking at. If you found anything smaller, move the element right before that, or right after that, and shift anything larger to the right. Let's take a look. We'll start with the first and compare everything to its left. This step is pretty easy. There's nothing larger than this element to its left, because there's nothing to its left. Now we consider the next element. The red element we're comparing to is not bigger than the green subject. So these two are already sorted. We don't need to move anything here. On to the next green subject. We compare each of these, and they're both smaller. Next. Okay, so this one's bigger, but so is this one and this one. So now we're going to perform this shift. Now the first four elements are all in order. We'll repeat this until the whole set is sorted. Let's speed through that. Insertion sort operates in quadratic time, both for big O, the upper bound, or the worst case, and the average case. It also has the same lower bound, the linear time. Because of the inherent lossiness of this big O notation, it ignores the fact that insertion sort tends to be pretty much faster than bubble sort in any case. Let's take a look here. You can see that it's doing very well on this nearly sorted set. It's already finished. Because of this, insertion sort is sometimes used as a finishing step for quicksort, which we'll look at next. It shares the benefit bubble sort has of returning an already sorted set in linear time. You can see that it's working through the reversed set, and it's doing better than bubble sort did on that, despite having the same complexity representations. In fact, it's working better on everything. We'll almost finish watching this before I change the slide. Quicksort's often considered to be the state-of-the-art in sorting algorithms. This is because the average case performance is very low for comparison sorting algorithms. Quicksort's algorithm is a bit different than bubble or insertion sort. Rather than moving the element we're comparing against, which we call the pivot in quicksort, and we use the green bar for. I'm sorry, we call the pivot in quicksort, but it's the subject that we were using the green bar for. We move everything else around to the left of it if it's less than the pivot, and to the right if it's greater than the pivot. We do the same thing for each subset until the entire set is merged. So here again, we've got our bars. For the algorithm to work, it doesn't actually matter what you pick for your pivot, but in practice, it makes sense to pick the midpoint because it tends to operate better for a lot of cases, especially for sorted data, which is one of quicksort's weaknesses because nothing will move as you pick different pivots. So we'll start with this bar and move all elements to the left or right of it based on whether they're taller or shorter. Since it was the tallest bar, we'll move everything else to its left, and it stays in the same order. Now we're going to quicksort everything to the left, which you can see here, and to the right, which is an empty set, so it doesn't get sorted. We'll pick a new pivot and move everything in the subset according to those same rules. Great, so this time we have both a left and a right set. The gray bar indicates that for now we're not considering that bar, either because it was already a pivot or because it's not in the subset being quicksorted. We'll again quicksort the bars to the left of the old pivot by choosing the midpoint as our new pivot. And we're just going to continue this. No music this time, it wouldn't last long enough. Quicksort is quick. But surprisingly, quicksort's big O is quadratic, just like insertion or bubble sort work. In the case of quicksort, it's extremely unlikely that you'll actually get this. To be quadratic time, you need to always pick a pivot that is the largest or smallest element, such that the remaining subsets are going to be of size n-1, so everything in the set except for that, and of size 0. We actually saw this already when the first pivot we chose was the largest, and we ended up with a set that was everything except for the pivot and an empty set. The magic of quicksort is that in the average case, unlike n squared, which was insertion and bubble sort, it performs linear arithmetically, which is linear times logarithmic. It's just a fancy word for n log n. And the average time here is not just intuition, like, on a random set it'll probably be this speed. There's actually several mathematical proofs for this, but they're over my head and out of scope. Linear arithmetic is also best case of n log n for quicksort. So while it's not always the fastest algorithm, and it can be just as slow as insertion or bubble sort depending on the inputs, quicksort is faster in the average case. For general purposes, meaning integers, strings, whatever, this is the cream of the crop because those need to be operated on using a comparison sort, and something like integers could use a specialized sort that deals with only numbers. That said, it does have its weaknesses. Well, you can see that it's great on the random and nearly sorted sets. It has trouble, it does great on the random and reverse sets, but it has trouble with the nearly sorted and few unique sets. So let's take a look at all of these algorithms next to each other. Bubble on top, then insertion, then quicksort. As the different algorithms work and finish, you can begin to see that some are better suited for specific tasks. The random set in the first column is a good approximation of the average case, and quicksort did the best there. It also makes short work of the reverse set, which trips up a lot of sorting algorithms. Insertion sort works very quickly for the nearly sorted set. And even bubble sort is going to do better than quicksort did on that. None of these algorithms work that great with the few unique set. But the most important thing is that quicksort works best on the average random set. And that's why it is used as Ruby's sort algorithm. I'd like to thank my employer, Heroku, for supporting me in coming to MagmaConf this year. You may have heard about our new automated certificate management offering, which gives you free Let's Encrypt certificates for paid dynos. This video shows how easy it is. Let's say order of 1 complexity. You should check it out if you haven't. Gracias. Thank you so much, Caleb.
Hello. Yes. Awesome. Thank you. Thank you so much, Caleb, for your talk. I don't know if you have any questions from the audience. Yes, we have one. There's someone going to you with a microphone right now.
Are there built-in ways to use other algorithms other than quicksort without having to write it yourself?
Ruby only uses quicksort, but it does a different variant of quicksort depending on some inputs. I tried to look at it, but it's this second slide here, and it's way too complicated for me.
So it's not at the Ruby API level of abstraction, they don't expose the
The question is, at the Ruby level of the abstraction, can you change the sorting algorithm when you call sort? And the answer is no.
Any other questions? No?
Thanks a lot.
Okay, thank you so much, Caleb. I'm going to give you your questions.
Oh, wait.
Okay, and moving on, are you shaking my hand? Really? Okay, sure, why not? Moving on to our next